Hello and welcome to Late Night Space. Before settling in, take a quiet moment to like the video and subscribe to the channel. It helps this calm little corner of the universe reach other nighttime listeners who enjoy steady, thoughtful space stories. And if you'd like, leave a comment sharing where you're watching or listening from. It's always fascinating to see just how widely spread this small community is across the planet. Because wherever you are above your galaxies, they feel permanent, ancient, immovable. Vast spirals of starlight suspended in darkness, so enormous that even light takes tens of thousands of years to cross them. It is easy to assume they have always been there, scattered across space like eternal islands. But they have not. There was a time when the universe held no galaxies at all. No spirals, no glowing cores, no sweeping arms of stars, only a smooth, almost featureless sea of hot plasma expanding into darkness. No structure, no shape, no grand cosmic architecture, just simplicity. And then, slowly, almost imperceptibly at first, something changed. Tiny variations in density, differences so small they were once measured as barely 1 part in 100,000, began to grow. Gravity, patient and relentless, started to gather matter together. Invisible scaffolding made of dark matter began forming the framework. Hydrogen gas drifted inward. The first stars ignited. Light returned. But none of it happened quickly. Galaxies were not born in a flash. They did not appear fully formed. They assembled piece by piece over hundreds of millions and then billions of years. They merged, they collapsed, they reignited, they evolved. The birth of galaxies was slow. Tonight, the story drifts back across cosmic time to that gradual transformation, from smoothness to structure, from darkness to light. From simple gas to vast spirals holding hundreds of billions of stars. The sky may look still, but every galaxy within it is the result of a long and delicate process, shaped by gravity, cooled by time, and sculpted by forces that are still at work even now. So allow the pace of the universe to set the rhythm. As the world quiets, attention can gently turn outward, toward the slow birth of galaxies. The sky may look still, but the calm up there is deceptive. Those quiet spirals and glowing smudges of light feel permanent, as if the universe has always been arranged into islands of stars. Yet the earliest universe had no galaxies at all. No disks, no cores, no sweeping arms of starlight. Just an expanding, cooling cosmos that, at first glance, was almost perfectly smooth. To find the beginning of the story, it helps to drift back to a time when the universe was young enough to be simple. Roughly 380,000 years after the Big Bang, space had expanded and cooled to the point where charged particles could finally settle down. Before this moment, the universe was filled with a hot plasma of free electrons and protons. Light could not travel far because photons scattered constantly off those free charges, like trying to shine a torch through thick fog. Then, as the temperature fell, electrons combined with protons to form neutral hydrogen atoms. With fewer free charges to scatter off, photons suddenly had room to move. The universe became transparent. That first freely traveling light still exists today. It has been stretched by the expansion of space into microwave wavelengths, becoming what is known as the cosmic microwave background. It is not a metaphor or a poetic idea. It is a measurable glow coming from every direction. The oldest light that can be observed directly. It was first detected in 1965 by Arno Penzias and Robert Wilson. Later, it was mapped in increasing detail by NASA's Wilkinson Microwave Anisotropy probe, and with even finer precision by the European Space Agency's Planck satellite. When Planck looked at the cosmic microwave background, it revealed something that sits at the heart of galaxy formation. The early universe was astonishingly uniform, but it was not perfectly uniform. Across the whole sky, Planck measured tiny temperature variations, differences on the order of 1 part in 100,000. These were not random speckles. They were a fingerprint of the early universe, a pattern that tells a story about where matter was slightly denser and where it was slightly thinner. Those tiny variations mattered because gravity is a patient force that does not need drama to begin working. A region that is only slightly denser than its surroundings has slightly stronger gravity. That extra pull attracts a little more matter. With more matter comes stronger gravity, which attracts more matter still. This is gravitational instability, the simplest engine of structure formation. It is not fast, it is not flashy, but given time, it is relentless. The fact that there were any fluctuations at all leads into one of the most important ideas in modern cosmology: cosmic inflation. In the early 1980s, physicist Alan Guth proposed that the universe underwent a brief period of extremely rapid expansion in the earliest fraction of a second. Inflation helps explain why the universe looks so smooth on large scales, while still containing the slight irregularities needed for structure to form. The idea is that tiny quantum fluctuations, normally confined to microscopic scales, were stretched to enormous sizes by inflation, and then imprinted into the distribution of matter and radiation. The cosmic microwave background carries the result of that imprint, like a fossil record written in temperature. None of this requires the universe to be chaotic. In fact, the astonishing thing is how calm the beginning seems. The early universe was smooth enough that the largest structures visible today had to grow from almost nothing. And that tells a listener something important right away. Galaxies were never going to appear quickly. When the initial differences are that small, the work of gravity takes time. Gravity itself is described most fundamentally on cosmic scales by Albert Einstein's general theory of relativity. In this framework, mass and energy curve space-time, and matter follows that curvature. In slightly denser regions of the early universe, space-time curvature was slightly deeper, and matter drifted inward. In slightly emptier regions, matter drifted away. Over long spans of cosmic time, the dense regions became denser, and the empty regions became emptier. That is how a smooth universe begins to develop texture. But there was an obstacle. In the early universe, ordinary matter, the kind made of protons and neutrons, did not have complete freedom to clump. It interacted with radiation strongly. In the earliest times, radiation pressure resisted collapse. Even after the universe became transparent and neutral hydrogen formed, the ordinary gas still had to cool and settle, and cooling was limited by its simple chemistry. If galaxy formation relied only on ordinary matter, it would have struggled to build structure fast enough to match what is observed today. This is where the second foundation of the story appears: dark matter. Dark matter is not seen directly. It does not shine. It does not absorb light. It does not scatter light in the way ordinary matter does. Its presence is inferred through gravity. The idea became overwhelmingly persuasive through multiple lines of evidence, including the work of astronomer Vera Rubin, and her colleague Kent Ford in the 1970s. They studied how spiral galaxies rotate, measuring the speeds of stars and gas at different distances from galactic centers. If most of the mass were in the luminous matter, rotation speeds would fall with distance because the gravitational pull would weaken. Instead, Rubin and Ford found that rotation curves were flat. Stars far from the center were orbiting too quickly to be held in place by visible matter alone. The simplest conclusion was that galaxies sit inside massive halos of invisible matter. That invisible component changes everything about the early universe because dark matter behaves differently from ordinary gas. Dark matter does not feel radiation pressure in the same way. It does not need to cool by emitting light. It can begin clumping earlier and more effectively, responding almost purely to gravity. When the universe was still young, dark matter started to gather into slightly denser regions that corresponded to the tiny fluctuations imprinted in the cosmic microwave background. Over tens of millions and then hundreds of millions of years, those dark matter overdensities grew. They formed gravitational wells called dark matter halos, invisible structures that would later cradle galaxies. The most important thing about a dark matter halo is not its appearance, because it has none in the usual sense. The important thing is its gravity. A halo is a reservoir of mass that deepens the local curvature of space-time, providing a place where ordinary gas can fall in, collect, and eventually form stars. This process can be explored not only with telescopes, but with computation. Large cosmological simulations, such as the Millennium Simulation, carried out by researchers associated with the Max Planck Institute for Astrophysics, model billions of particles representing dark matter and let them evolve under gravity in an expanding universe. When this is done, a striking pattern emerges again and again. Dark matter does not form isolated clumps scattered evenly like raisins in a loaf. It forms a cosmic web, filaments stretching across space, dense nodes at filament intersections, and enormous voids between them. Galaxies form where the web is thickest, because that is where gravity concentrates matter most effectively. The cosmic web is not a decorative phrase. It is a real, measurable feature of the universe. When astronomers map galaxies across huge volumes of space, they find that galaxies themselves trace a filamentary pattern remarkably similar to the one predicted by dark matter simulations. This is one of the reasons dark matter is treated not as a speculative add-on, but as a core ingredient of the standard cosmological model. Once dark matter halos formed, ordinary matter began to respond more dramatically. Gas fell into the gravitational wells, but gas, unlike dark matter, brings thermodynamics with it. When gas falls inward, it accelerates under gravity, and as it compresses, it heats up. That heating increases pressure, which resists further collapse. For gas to continue sinking deeper into a halo and forming denser structures, it must lose energy. It must cool. And cooling in the early universe was slow. Even so, the presence of dark matter halos changed the pace of the entire story. Halos created deeper potential wells than ordinary matter could have produced alone in the same time. They acted as gravitational scaffolding. Ordinary gas could fall into those wells, collect and build up in density. Over time, the densest regions within halos became sites where gas could eventually cool enough to collapse further and ignite the first stars. This is why the birth of galaxies is often described as hierarchical. Small halos form first. Those halos merge into larger halos, Ordinary matter follows, collecting and growing in mass as the halos deepen. The universe does not begin with large galaxies. It begins with many small structures that assemble into larger ones over cosmic time. As halos merge, they do not collide like solid objects. They interpenetrate and relax into new distributions, with gravity redistributing energy and angular momentum. A merged halo becomes larger, deeper, and more capable of holding onto gas. It can pull in additional material from surrounding filaments. It can retain heated gas more effectively, allowing cooling to proceed over longer periods instead of being easily disrupted. In this way, dark matter does not merely help galaxies form. It shapes where they form, how they grow, and how their environments are structured. A galaxy is not simply a cloud of gas that happened to collapse. A galaxy is the luminous component of a much larger dark matter system. The stars are the visible frosting, but the cake is mostly invisible. Observationally, the influence of dark matter extends beyond rotation curves. Gravitational lensing, where mass bends light from background objects, reveals that clusters of galaxies contain far more mass than their luminous matter accounts for. The pattern of lensing maps out mass distributions consistent with large amounts of dark matter. Even the cosmic microwave background itself, measured by Planck, encodes the effects of dark matter through the way it influences early acoustic oscillations in the primordial plasma. Different amounts of dark matter change the characteristic peaks in the cosmic microwave background power spectrum. The measured pattern is one of the reasons cosmologists can estimate the universe's composition so precisely. But the most quietly powerful consequence of dark matter for this story is time. Dark matter allows structure to form gradually but efficiently. It accelerates the growth of the seeds without requiring the universe to be born clumpy. It lets a nearly uniform universe become a structured one, slowly, through the steady amplification of tiny differences. If a listener imagines the early universe as perfectly smooth, galaxy formation becomes almost impossible to picture. But if the listener imagines the early universe as nearly smooth, with tiny ripples recorded in the cosmic microwave background, the process becomes clear. Gravity amplifies those ripples. Dark matter responds first and builds scaffolding. Ordinary matter follows heating and cooling, sinking deeper into the scaffolding over time. That slow gathering is the first real motion toward galaxies. The universe did not begin with spirals and glowing bulges. It began with a faint pattern in an ancient sea of light, and with invisible matter quietly assembling into halos across expanding space. Over hundreds of millions of years, those halos grew along filaments of the cosmic web, merging and deepening. Ordinary gas collected inside them, waiting for cooling to make the next step possible. From a distance, it might sound like nothing is happening, but in cosmic terms, everything is beginning. The smooth universe is breaking its symmetry, not with a sudden crack, but with a slow, patient drift. Gravity is gathering. Dark matter is building structure in the dark. And in the densest parts of those invisible wells, the raw material of galaxies is finally starting to pile up. With dark matter halos in place, gravity finally had something like a stage. Not a solid stage, not a surface, but a framework of potential wells, deep enough to gather ordinary gas and hold it there. The universe was still expanding, still stretching the distances between faraway regions, But inside these overdense pockets, expansion no longer had the final say. Gravity began to win locally, not by stopping the expansion everywhere, but by carving out exceptions to it. This is one of the most important ideas in galaxy formation. The universe can expand overall while still allowing structures to collapse in specific regions. Expansion is the growth of space itself on very large scales. Collapse is what happens when mass concentrates enough for gravity to pull matter inward faster than expansion can pull it apart. A dark matter halo is, in a sense, a region where gravity has negotiated a private agreement with the universe. Out there, everything keeps stretching, but in here, matter is allowed to gather. As gas fell into a halo, it did not arrive politely. It accelerated, it streamed along filaments of the cosmic web and plunged into the halo's gravitational potential. When those streams met, they formed shocks, abrupt transitions where infalling material was slowed and heated. This heating is not a side effect, it is central. Gravity does not simply pull matter inward, it converts gravitational potential energy into thermal energy. The deeper the potential well, the more energy is released as gas falls in, and the hotter the gas becomes. Hot gas pushes back. Thermal pressure is the enemy of collapse. A gas cloud that becomes too hot resists further compression because its particles move faster and collide more vigorously, producing an outward pressure that counters gravity. So the story becomes a balance between two forces that are always negotiating. Gravity pulling inward, pressure pushing outward. Gravity can gather gas into halos, but it cannot easily force that gas all the way into dense star-forming regions, unless the gas finds a way to shed its heat. That is where cooling becomes the slow heartbeat of galaxy formation. In the early universe, the gas was nearly pristine. It was mostly hydrogen and helium, created in Big Bang nucleosynthesis within the first few minutes after the Big Bang. There were essentially no heavy elements at first, because heavy elements are made inside stars. Without stars, there is no carbon, no oxygen, no silicon, no iron. This matters because heavy elements are exceptionally good at radiating energy away. Their complex electron structures provide many ways for energy to leave a gas cloud as light. A universe made of only hydrogen and helium is a universe where cooling is possible, but limited. So when gas fell into early halos, it heated up and then struggled to cool down. The ability of gas to cool depends strongly on temperature. At temperatures around 10,000 degrees Kelvin, atomic hydrogen can cool efficiently by emitting radiation through electron transitions. In simple terms, hydrogen atoms can be excited by collisions and then emit photons as they relax to lower energy states. That emitted light carries energy away, allowing the gas to cool. This is one reason certain halo masses become important. If a halo is massive enough that infalling gas is shock heated to around 10,000 degrees Kelvin, atomic hydrogen cooling turns on robustly, and gas can begin settling more effectively toward the center. But in smaller halos, gas may not reach those temperatures, and cooling can be much less efficient. In those cases, a different coolant becomes essential: molecular hydrogen. Molecular hydrogen is a fragile but powerful molecule in primordial conditions. It forms when two hydrogen atoms bind together, usually through reaction pathways involving a free electron as an intermediary. Even a small abundance of molecular hydrogen can allow gas to radiate energy at lower temperatures, than atomic hydrogen cooling can manage. This enables gas to cool from thousands of degrees down toward a few hundred degrees, which greatly reduces thermal pressure and allows gravity to compress gas to higher densities. However, molecular hydrogen is easily destroyed by ultraviolet radiation. As the first stars begin to appear, they can suppress molecular hydrogen formation in nearby regions by breaking those molecules apart. This creates an early example of feedback, where the first luminous objects influence the ability of other regions to form stars. Galaxy formation is never purely one-directional. Every new source of light reshapes the conditions around it. Even before widespread starlight, the cooling pathway itself was slow. Forming molecular hydrogen takes time, and the amount available depends on the local abundance of free electrons, the density of the gas, and the radiation environment. Cooling, therefore, becomes the bottleneck. Gas can be gathered by gravity, but the pace at which it can collapse into dense star-forming clouds is controlled by how quickly it can lose energy. This is why the birth of galaxies is a story of patience. Gravity can pull. But cooling decides whether the pull leads to a compact, dense structure or a puffy, hot reservoir that takes hundreds of millions of years to settle. There is another key threshold that helps make sense of when collapse proceeds: the Jeans instability, described by the British physicist Sir James Jeans. Jeans showed that there is a critical scale at which a gas cloud becomes gravitationally unstable. If a region of gas is too hot or too diffuse, pressure can support it against collapse. If it becomes cool and dense enough, gravity overwhelms pressure and collapse begins. Put plainly, the requirement is this: a region collapses when its inward gravitational pull exceeds its outward thermal pressure. That sounds simple, but the implications are enormous. Cooling lowers temperature. Lower temperature lowers pressure. Lower pressure means smaller regions can collapse. So cooling does not just allow collapse, it determines the size scale of collapse. In primordial gas, where cooling is limited, collapsing regions tend to be large. Later, when heavy elements are present, cooling becomes more efficient, and gas can fragment into much smaller clumps. That shift changes the typical masses of stars and the efficiency of star formation, and it ripples forward into the entire evolution of galaxies. In the earliest halos, as gas cooled gradually, it began to settle toward the center. But it did not fall straight in. It rotated. Even small amounts of angular momentum matter because angular momentum is conserved. Gas collapsing inward spins faster as it contracts, which creates a kind of rotational support. This is one of the reasons galaxies often develop disks later on. Rotation helps flatten gas into a plane. But at this stage, the disk is not yet a calm spiral structure. It is more like a turbulent, thick, rotating reservoir, fed by inflows from the cosmic web and disturbed by mergers. Mergers are constant in this era. Dark matter halos merge, and the gas inside them responds. When halos combine, their gas reservoirs can be stirred violently. Streams collide, shocks form, and fresh gas may be driven toward the center. In some cases, mergers can compress gas and trigger bursts of star formation once stars are possible. In other cases, mergers can heat gas and delay collapse. The outcome depends on mass ratios, geometry, and the gas fraction of the systems involved. Galaxy formation is messy, but the mess has rules. Those rules include timescales, and the timescales are long. A major halo can take hundreds of millions of years to assemble through mergers and accretion. Gas can take comparable times to cool and settle, especially if it is repeatedly heated by shocks, ultraviolet radiation, or later by supernova explosions. The listener's sense of time has to stretch here. In human terms, 1,000,000 years is unimaginable. In galaxy formation, 1,000,000 years can be a brief pause between events. As halos grow larger, a new cooling regime becomes more important. In more massive halos, gas can be heated to millions of degrees Kelvin, becoming a hot, diffuse halo atmosphere. Cooling such gas can take a long time depending on density and metallicity. In the modern universe, massive galaxies and galaxy clusters often contain large reservoirs of hot gas that cool slowly. In the early universe, once halos reached sufficient mass, similar hot atmospheres could form. This created another way in which growth can slow. A deep gravitational well can hold onto gas, but that gas may be too hot to form stars efficiently until it cools. So gravity both enables and complicates. It builds the well, but it heats the gas. This is the central tension of the slow birth of galaxies. The universe provides a force that gathers matter, and the act of gathering creates heat that resists further gathering. The escape route is radiation. A gas cloud must glow away its energy, photon by photon, until it is cool enough to collapse further. The first time this begins to work reliably is when halos reach masses where cooling becomes effective enough to sustain collapse. In the earliest phases, these halos were small, and molecular hydrogen was essential. Later, as halos grew, atomic cooling became dominant in many regions. This transition helped increase the efficiency of gas settling and star formation. But even then, collapse is not a straight line from gas to stars. Gas must fragment. Fragmentation depends on turbulence, density structure, and cooling. Regions of higher density cool faster because cooling rates often increase with density. This can create runaway effects where dense clumps become denser, while diffuse gas remains hot. Over time, these dense clumps can become the seeds of the first star-forming regions. It is also important to remember that not every halo successfully forms stars early. Some halos may remain dark, containing gas that never cools sufficiently, or that is heated and stripped by radiation from nearby star-forming regions. Others may form a small number of stars and then be quenched temporarily by feedback. This unevenness is part of why the early universe is not a uniform field of glowing objects. It is patchy. Some regions light up earlier, some stay dark longer. The slow birth happens in waves. At this point, the universe is still young enough that everything is close to its starting conditions. The cosmic microwave background has already streamed away, but its imprint remains in the distribution of matter. The cosmic web is thickening. Halos are merging. Gas is falling in. Cooling is beginning to shape what happens next. The listener can imagine this as a vast, dark framework where matter is drifting along invisible pathways, pooling in deeper pockets, and then slowly, beginning to settle. The best evidence that this picture is broadly correct comes from the convergence of theory, simulation, and observation. Simulations based on cold, dark matter and gravitational instability produce a cosmic web that resembles what galaxy surveys actually observe. Measurements from the Planck satellite constrain the initial conditions, showing that the early fluctuations are indeed small enough to require long timescales for growth. Observations of high redshift galaxies with the Hubble Space Telescope and the James Webb Space Telescope show that small galaxies appear early, consistent with hierarchical formation. But the exact details of cooling and early star formation remain a field of active research, because cooling is where microphysics meets cosmology. It is where atomic transitions, molecular chemistry, and radiation backgrounds determine the fate of a galaxy-scale structure. A small change in cooling efficiency can shift the timing of first star formation by tens or hundreds of millions of years. In the early universe, that is a meaningful difference. Still, the broad flow is clear. Gravity gathers matter into halos and along filaments. Gas falls in and heats up. Cooling allows gas to lose energy and reduce pressure. Reduced pressure allows collapse on smaller scales. Collapse becomes fragmentation, and fragmentation becomes the conditions for star formation. The slow birth of galaxies is not a failure of gravity to act quickly. It is the natural consequence of a universe where matter must radiate away energy before it can settle into the dense structures that eventually shine. And in the densest, coolest pockets of those early halos, the next transformation is waiting. The gas is nearing the point where it can finally collapse, far enough for the first stars to ignite, turning invisible scaffolding and dark reservoirs into something that begins, at last, to glow. The densest pockets of gas inside those early halos did not collapse politely. Once cooling had done enough work to lower the temperature and reduce pressure, gravity began to win on smaller scales, and the collapse accelerated. A cloud that has spent tens of millions of years hovering in a delicate balance can suddenly tip into a faster inward fall, not because gravity changes, but because the cloud finally stops pushing back as hard. Density rises, cooling becomes more effective, and the whole process feeds on itself. This is the moment when the universe starts to trade dark potential wells for actual light. The first stars were almost certainly unlike the stars seen in the Milky Way today. The early gas contained essentially no heavy elements, meaning it cooled less efficiently and fragmented into larger clumps. In modern star-forming regions, dust and metals help gas break into many small pieces, producing large numbers of low-mass stars. In the primordial universe, the gas tended to collapse into fewer, larger fragments. Theoretical models and numerical simulations developed by research groups at places such as the Harvard-Smithsonian Center for Astrophysics and the Kavli Institute for Cosmology suggest that the first stars, known as population 3 stars, were often very massive, sometimes tens of times the mass of the Sun, and in some cases, perhaps even more. Massive stars live fast. They burn their fuel at a furious pace because their cores are hotter and denser, which accelerates nuclear fusion. A star like the Sun shines steadily for billions of years, but a star tens of times more massive can exhaust its core hydrogen in only a few million years. These early giants would have been intensely luminous and extremely hot, producing large amounts of ultraviolet radiation. In a young universe that had recently emerged from darkness, those photons mattered as much as the stars themselves. Inside a star, energy is produced by nuclear fusion, and the basic engine begins with hydrogen becoming helium. The details were first worked out in a modern form by physicist Hans Bethe in the 1930s, who described the proton-proton chain and the carbon-nitrogen-oxygen cycle as pathways for hydrogen fusion. In metal-free population 3 stars, the balance of these pathways may have differed early on, but the outcome was the same. Hydrogen fused into helium, releasing energy that pushed outward as radiation pressure, holding gravity in check. This balance between outward pressure and inward gravity is what allows a star to exist as a stable object, rather than collapsing further. Gravity compresses the core, raising temperature. Higher temperature increases fusion rates. Fusion releases energy, raising pressure. Pressure pushes outward against gravity. For millions of years in a very massive population 3 star, this balance holds. Then the core hydrogen begins to run out. When hydrogen is depleted in the core, the star changes structure. The core contracts, heats further, and fusion moves to heavier fuels in layers, building helium into carbon and oxygen, then producing heavier elements in successive burning stages in the most massive stars. Each stage occurs faster than the last because heavier element fusion requires higher temperatures and yields less net usable energy. Eventually, the star develops an iron-rich core. Iron is a turning point because fusing iron into heavier elements consumes energy rather than releasing it. Once iron accumulates, fusion can no longer support the core. Radiation pressure falters. Gravity wins abruptly. The core collapses in a fraction of a second, and the result is a supernova explosion of extraordinary energy. Those first supernovae were more than spectacular endings. They were chemical beginnings. Before stars, the universe contained mostly hydrogen and helium. After the first supernovae, the universe began to contain carbon, oxygen, neon, magnesium, silicon, and iron. These elements were forged in stellar interiors and in the explosive conditions of the supernova itself, then thrown outward into surrounding space. For the first time, the gas between stars was enriched. The universe became chemically more complex, and that complexity changed the physics of cooling. Heavy elements provide many ways for gas to radiate energy away. Their electron structures allow a rich spectrum of emission lines, meaning a cloud can shed heat more efficiently across a range of temperatures. Even a small fraction of metals in a gas cloud can lower its temperature faster, allowing it to fragment into smaller clumps. That fragmentation shifts star formation toward lower masses. In other words, the first stars did not only light up the universe, they also rewrote the rules for what kinds of stars could form next. But there was another, even larger transformation happening at the same time. It was not only the gas inside halos that changed. The space between halos changed too. After recombination, when neutral hydrogen first formed, the universe entered a period often called the cosmic dark ages. This name is not dramatic, it is literal. There were no stars yet, no galaxies, and therefore no starlight. The only light left over from the early universe was the cosmic microwave background, which by then had redshifted into microwaves and no longer lit space in any meaningful visible sense. The universe contained matter, but it did not yet contain luminous structures. The first population 3 stars ended that darkness, but they did not merely illuminate their own neighborhoods. Their ultraviolet radiation carried enough energy to ionize hydrogen, stripping electrons away from protons. In regions around these stars, neutral hydrogen was turned back into ionized plasma. This process began the epoch of rhionization. Rhionization was not a single moment. It was a gradual transition that unfolded over hundreds of millions of years. It began locally, around the first stars and early protogalaxies, and spread outward as more sources of ultraviolet radiation appeared. Each star-forming region created a bubble of ionized hydrogen around it, a growing volume where photons could travel more freely without being absorbed by neutral atoms. As more bubbles formed, they expanded and eventually overlapped, turning the universe from mostly neutral back into mostly ionized. Evidence for reionization comes from several directions. Measurements of the cosmic microwave background made by the Planck satellite include information about how many free electrons existed along the line of sight, because free electrons scatter photons and leave subtle imprints in the polarization signal. Quasar spectra also provide a powerful clue. Quasars are extremely bright, active galactic nuclei powered by supermassive black holes. Their light travels through intergalactic space and passes through hydrogen along the way. Neutral hydrogen absorbs light at specific wavelengths associated with the Lyman alpha transition. At very high redshift, quasar spectra show strong absorption features, including what is known as the Gunn-Peterson trough, indicating that significant amounts of neutral hydrogen remained in the intergalactic medium early on. The picture that emerges is a universe that reionized gradually, with most of the process completing within roughly the first billion years after the Big Bang. The details, including the exact timeline and which sources dominated, remain an active area of research. Early massive stars likely played a major role, and later, small galaxies with sustained star formation may have contributed significantly, simply because they were numerous. Reionization also fed back into galaxy formation, shaping which halos could continue forming stars efficiently. Ionized gas is typically warmer than neutral gas, and warm gas has higher pressure. When the intergalactic medium is heated by ultraviolet radiation, it becomes harder for the smallest dark matter halos to pull gas inward. Shallow potential wells struggle to hold on to heated material. This means reionization can suppress star formation in low-mass halos by preventing gas from cooling and collapsing. In that sense, the first light did not only enable galaxies, it also imposed new limits on which regions could form them. At the same time, inside more massive halos, the combination of deeper gravity and improving cooling efficiency allowed star formation to become more sustained. Gas enriched with heavy elements cooled more effectively and fragmented into more numerous star-forming clumps. Instead of isolated, short-lived population 3 giants dominating the light, galaxies began producing broader stellar populations with a range of masses. Some stars were still massive and short-lived, driving supernova feedback and producing more metals. Others were lower mass and longer-lived, creating a growing background of steady starlight. This period marks the transition from a universe where stars are rare sparks to a universe where galaxies begin to act as persistent engines of light. Observationally, this transition is challenging to study because it occurs at extreme distances. Light from galaxies forming in the first few 100 million years after the Big Bang has traveled for more than 13 billion years to reach Earth. Yet telescopes have begun to reveal these objects. The Hubble Space Telescope detected galaxies at very high redshift, pushing the frontier deeper into cosmic time. The James Webb Space Telescope has extended this reach further, observing candidate galaxies at redshifts that correspond to a universe less than 1 billion years old, and in some cases even earlier. Some of these early galaxies appear surprisingly bright. That brightness could mean several things. It could indicate rapid star formation in dense, early environments, efficient cooling in certain halos, or less dust obscuration than in later epochs. It could also reflect the way the brightest objects are easier to detect, meaning the earlier surveys naturally find the most extreme examples first. Either way, these observations are reshaping the details of early galaxy formation while leaving the broad framework intact. Small structures form first, light returns gradually, and the universe becomes increasingly complex. The chemical consequences of the first stars also continue to ripple outward. Once metals are present, new cooling channels open, and gas can collapse to higher densities more readily. This changes not only the mass distribution of stars, but also the efficiency of star formation itself. It becomes easier for a given amount of gas to turn into a larger number of stars. In turn, those stars produce more metals. The universe enters a feedback loop of enrichment, where each generation makes the next easier to form. But feedback is not only chemical, it is also mechanical and radiative. Supernova explosions inject energy into surrounding gas. In small, early halos, a single supernova could have a dramatic impact, heating gas and driving winds that expel material from the halo entirely. This could temporarily shut down star formation by removing or heating the gas reservoir. Over time, as halos grew more massive, they became better at holding onto gas even in the face of supernova feedback. This is one reason galaxy formation becomes more stable and sustained in larger systems. Deep gravitational wells buffer against disruption. The interplay between star formation, supernova feedback, and halo growth is one of the reasons the birth of galaxies is slow. It is not a straightforward march from gas to stars. It is a cycle. Gas collapses, stars form, stars heat and disturb gas. Gas cools again. Collapse resumes. Over hundreds of millions and then billions of years, these cycles build galaxies. During rionization, the universe also becomes more transparent in certain ways. Once hydrogen is ionized, it does not absorb ultraviolet light in the same way neutral hydrogen does, making it easier for radiation to travel long distances. This changes the propagation of starlight and the thermal state of the intergalactic medium. It also affects how galaxies are observed because the amount of neutral hydrogen between a distant galaxy and Earth influences how much of its ultraviolet emissions survives the journey. At the same time, the cosmic web continues thickening. Dark matter halos keep merging and growing. Gas continues streaming along filaments into dense nodes. The first galaxies begin appearing not randomly but preferentially in regions where matter is concentrated. Rionization itself is therefore patchy, not only because star formation is patchy, but because structure is patchy. Dense regions light up earlier. Sparse regions lag behind. This gradual, uneven illumination creates a universe that is becoming structured in both matter and light. The density field becomes more contrasty as gravity amplifies overdensities and empties voids. The radiation field becomes more complex as bubbles of ionization expand and overlap. The chemical field becomes richer as metals spread outward from supernovae. Multiple maps of reality begin to separate from one another, and all of them evolve together. There is a quiet elegance to this stage. The first stars do not simply appear and vanish. They initiate a chain reaction of complexity. They turn pristine gas into enriched gas. They turn neutral space into ionized space. They transform invisible potential wells into luminous communities of stars. And still, it takes time. A few million years might be the entire lifespan of a massive population 3 star. But the transformation of the intergalactic medium through ionization takes hundreds of millions of years. The buildup of metals across wide regions takes similar spans. The assembly of persistent galaxies takes longer still. Even the spread of light across the cosmic web is slow, not because light moves slowly, but because the sources of light are assembling slowly. By the end of this phase, the universe is no longer in its earliest quiet darkness. It has gained a background of starlight. It has pockets of ongoing star formation. It has growing galaxies whose internal chemistry is becoming more diverse. It has an intergalactic medium that is increasingly ionized. The first stars have come and gone, but their influence remains everywhere, in the temperature of space, in the composition of gas, and in the very possibility of forming smaller, longer-lived stars. The slow birth of galaxies depends on these first flashes, not because galaxies are born in a single blaze, but because the first blaze changes what is possible afterward. It turns a simple universe into one that can build complexity more easily, generation by generation, across the long, patient stretch of cosmic time. As ionization spread and heavy elements began to lace the gas between halos, the first galaxies stopped being rare sparks and started becoming a population. Not a neat, orderly population, but a real one. Across the densest parts of the cosmic web, many dark matter halos now contained enough cooling gas, enough metals, and enough repeated star formation to build something that could reasonably be called a galaxy, even if it would look unfamiliar to anyone used to the calm symmetry of modern spirals. These earliest galaxies are often described as proto-galaxies, and the word fits because they were still assembling their identity. They were smaller than most present-day galaxies, often irregular, clumpy, and intensely active. Their star formation was not evenly spread across a tidy disk. It erupted in dense pockets where gas had cooled into molecular clouds, then faded when feedback heated or expelled that gas. In many cases, star formation occurred in bursts rather than in a steady, gentle flow, because young galaxies were constantly being jostled by infalling material and frequent interactions. A protogalaxy is not just a pile of stars. It is a dynamic system made of dark matter, gas, stars, and radiation. Dark matter provides the dominant mass and the gravitational potential well. Gas provides the raw material for new stars. Stars provide light, heavy elements, and feedback. Radiation shapes the temperature and ionization state of the gas. Even in these early systems, the pieces already form a loop. Gas collapses into stars. Stars change the gas. Changed gas alters the next round of star formation. The way these proto-galaxies grow is strongly shaped by hierarchical structure formation in the cold, dark matter model. Small halos form first. They merge to form larger halos. The luminous galaxies within them follow the same pattern, building mass by both accreting gas and merging with other small galaxies. This makes the early universe a busy place. While the overall cosmos expands, dense regions behave more like crowded neighborhoods, with streams of gas feeding halos along filaments and small galaxies frequently interacting. When a proto-galaxy accretes gas from the cosmic web, it is often fed by narrow streams that can penetrate deep into the halo, especially at high redshift when the universe was denser. This gas is not always shock-heated into a smooth, spherical atmosphere. In many cases, it arrives as colder, denser flows that can deliver material efficiently to the central regions where stars form. The result is rapid growth, but still not instant growth. Even the most direct inflows take time to spiral inward, dissipate energy, and settle into star-forming clouds. At the same time, mergers remain common. When two small galaxies approach one another, their dark matter halos interpenetrate and eventually relax into a larger halo. Their gas clouds collide, compress, and heat. Their stars, which rarely collide directly, feel rapidly changing gravitational potentials that can distort orbits and pull out long tidal features. The overall effect is often messy and luminous, with enhanced star formation triggered by compression in the gas. Yet even in this chaos, something quietly consistent begins to emerge: rotation. A galaxy does not need to be large to rotate. It only needs a small net angular momentum, and the universe is generous with small asymmetries. In the early cosmic web, halos experience tidal torques, gravitational pulls from neighboring overdensities that twist and spin them slightly as they grow. This process is described in what is known as tidal torque theory, a framework that explains how collapsing regions acquire angular momentum before they fully detach from the general expansion. The rotation is not dramatic at first, but angular momentum is conserved, and conservation turns small beginnings into important consequences. When gas falls into a halo, it loses energy through radiation and shocks, but it does not easily lose angular momentum. As it contracts inward, its rotation speed increases. The result is a gradual flattening. Instead of collapsing into a sphere, the gas settles into a rotating structure, building a disk. This is not a decorative detail. It is a direct outcome of physics. A rotating system that cools tends to flatten because rotation provides support in the plane perpendicular to the axis of spin. In early proto-galaxies, disks are often thick, turbulent, and unstable compared to the thin, graceful disks seen in many nearby spiral galaxies. High accretion rates, frequent mergers, and intense star formation all stir the gas. Turbulence increases pressure support and can keep disks puffy. Feedback from supernova explosions can punch holes in the gas and drive outflows. Even so, the overall angular momentum structure tends to organize gas into a rotating configuration. This gradual emergence of disks is one of the reasons the birth of galaxies is slow. A disk is not something that appears fully formed. It is something that develops as gas accretes, cools, and redistributes angular momentum over many orbital times. An orbital time in a galaxy can be hundreds of millions of years in the outer regions. Even in smaller early galaxies, it is not short. The disk must be built over repeated cycles of inflow, cooling, star formation, and resettling. As gas collects in a rotating disk, the disk becomes a site of ongoing star formation. Dense regions form where gas is compressed by gravitational instabilities and turbulence. The disk can become unstable to fragmentation, forming giant star-forming clumps. In many young galaxies, these clumps are not small. They can contain enormous amounts of gas and form stars rapidly, then migrate inward over time, contributing to the growth of a central bulge. The balance between disk growth and bulge growth is influenced by interactions. A quiet disk, fed gently by gas accretion, can remain disk-dominated. A disk repeatedly shaken by mergers can be heated, thickened, or even transformed into a more spheroidal system. This is why morphology, the shape of galaxies, is tied so deeply to environment and merger history. Disk building is a slow craft. Mergers are the sudden interruptions that can either add material or rearrange the entire structure. Even when a disk survives, it does not necessarily look like a modern spiral. Spiral structure itself is a subtle phenomenon. If spiral arms were made of the same stars permanently arranged into a spiral pattern, differential rotation would quickly wind them up like a tightened spring. Inner stars orbit faster than outer stars, so fixed patterns would not last long. Yet spiral arms persist in many galaxies for billions of years, which suggests they are not fixed material structures. One important explanation is density wave theory, developed by C.C. Lin and Frank Hsu in the 1960s. In this framework, spiral arms are not collections of the same stars. They are regions of enhanced density that move through the disk, similar to a traffic jam that travels along a highway even as individual cars enter and leave it. Gas flows into these density enhancements, is compressed, and forms stars. The brightest, youngest stars then light up the arm, while older stars drift away. The arm persists as a pattern, not as a permanent arrangement of specific objects. In early galaxies, spiral patterns may be less stable and more transient because disks are more turbulent and clumpy. Yet the same underlying physics applies. Rotation and gravity shape the disk. Instabilities and density patterns compress gas. Star formation traces these compressions. Over time, as galaxies grow and disks become more settled, more persistent spiral structures become possible. The connection between rotation and mass is also a key observational bridge between theory and the real universe. Rotation curves, the way orbital speed changes with distance from the center, reveal that visible matter alone cannot account for the gravitational pull in galaxies. This is the evidence that drove the work of Vera Rubin and others. It also leads to a broader relationship known as the Tully-Fisher relation, discovered by astronomers R. Brent Tully and J. Richard Fisher in the 1970s. In plain terms, this relation shows that brighter spiral galaxies tend to rotate faster, linking luminous output to total mass, including dark matter. It is one of the ways astronomers connect the visible disk to the invisible halo. Proto-galaxies, then, are not just early galaxies in a smaller form. They are early galaxies in a different regime. Their gas fractions are higher. Their accretion rates are higher. Their environments are more interactive. Their feedback is more disruptive relative to their shallower gravitational wells. Their disks, when present, are often thicker and more unstable. Yet within them, the same ingredients that shape galaxies today are already present, and they are already beginning to organize into familiar patterns. Observations support this picture, even with the difficulty of looking so far back in time. The Hubble Space Telescope revealed many high redshift galaxies that appear small, irregular, and clumpy. The James Webb Space Telescope has pushed these observations further, detecting galaxies at redshifts corresponding to times when the universe was less than 1 billion years old. Many of these systems show signs of intense star formation and irregular structure, consistent with rapid growth and frequent interactions. Some appear more massive or more mature than earlier expectations, which has sparked discussion about how quickly gas can cool and form stars in the densest early halos, and whether early star formation efficiencies were higher than some models assumed. Even within uncertainty, the broad trajectory remains steady. Small galaxies form early. They merge. They accrete gas. They build rotating structures as angular momentum accumulates. They form stars in bursts and waves. Over time, some begin to develop disk-dominated shapes. Others, especially those battered by frequent major mergers, grow into more spheroidal systems. A quiet irony sits here. The shapes that look the calmest in the modern universe, like a smooth, symmetrical disk with elegant spiral arms, often require long stretches of relative stability to develop. They are the result of a galaxy not being disturbed too violently for a long time, allowing gas to settle and rotation to organize. Meanwhile, the most chaotic early systems are the ones actively building mass quickly, colliding, accreting, and lighting up in bursts. The universe, in its youth, tends to be productive in a slightly unruly way. All of this is still guided by the same fundamental pace setter: time. Rotation needs many orbital periods to shape a disk. Gas needs time to cool and settle. Clumps need time to migrate and merge. The halo needs time to grow through accretion and mergers. A protogalaxy may change its appearance dramatically over 1 billion years, but it will do so through many smaller events, each unfolding over tens or hundreds of millions of years. So when the first true galaxies begin to appear in recognizable form, it is not because the universe suddenly learned a new trick. It is because gravity and angular momentum have had enough time to sculpt matter into rotating systems, and because earlier generations of stars have had enough time to enrich gas so it can cool efficiently. The cosmic web provides the supply lines. Dark matter provides the wells. Cooling provides the settling. Rotation provides the shape. And in that slow convergence of forces, the universe begins to produce the first hints of the galaxies that will later feel so permanent, so ancient, and so quietly at home in the dark. A rotating disk is a patient structure. It takes time for gas to settle, for angular momentum to organize motion into a plane, and for star formation to become something like a steady rhythm rather than a series of shocks. But the early universe was not always patient in return. Galaxies grew in crowded parts of the cosmic web, and crowded places produce encounters. When galaxies meet, gravity does not simply add their masses together like stacking stones. It rearranges them. It can erase order, scramble orbits, and build a different kind of galaxy entirely. The most dramatic examples are major mergers, collisions between galaxies of roughly comparable mass. In the hierarchical picture of galaxy formation, these events are not rare accidents. They are expected milestones. Two similar halos drift together, their galaxies follow, and the interaction begins long before the stellar disks touch. Tidal forces stretch both systems. Stars are pulled into arcs and streams. Gas is compressed and shocked. The galaxies can pass through each other, separate, then return for another encounter. This dance can last hundreds of millions of years, sometimes longer, with each close pass stripping away more of the original structure. During these encounters, something profound happens to the orderly rotation that defines a disk. A spiral galaxy's stars mostly follow coherent orbits in a plane. In a major merger, the gravitational potential changes rapidly and repeatedly. Orbits are torqued, tilted, and scattered. The process that redistributes orbital energies and directions is often described as violent relaxation, a term introduced by Donald Lynden Bell in the 1960s. The word violent refers to the rapid change in gravitational conditions, not to collisions between stars. Stars almost never hit each other directly. Space is far too empty for that. Instead, stars respond to gravity's reshuffling, and their collective motion becomes more randomized. When the dust settles, the remnant is often an elliptical galaxy. Elliptical galaxies are not flat disks with spiral arms. They are three-dimensional swarms of stars, held up not by organized rotation, but by the random motion of stellar orbits in many directions. Their light profiles are smooth. Their shapes range from nearly spherical to elongated ellipsoids. Many contain old stellar populations, suggesting that their most intense star formation occurred long ago, often in bursts associated with mergers. In the modern universe, elliptical galaxies are common in dense environments, especially in the centers of galaxy clusters, where repeated interactions over billions of years make orderly disks harder to preserve. Edwin Hubble's early 20th century classification scheme, often called the Hubble sequence, placed ellipticals on one end and spirals on the other, as if they were separate species. Modern galaxy formation treats them more like outcomes of history. A disk is what forms when gas accretes gently and rotation remains intact. An elliptical is what often forms when major mergers repeatedly disrupt that rotation and consume or heat the available cold gas. Gas behaves very differently from stars during a merger, and this difference explains why mergers can be so bright. Stars are essentially collisionless, sliding past each other under gravity. Gas clouds do collide. They compress. Compression triggers star formation. The merger funnels gas inward through gravitational torques that remove angular momentum from the gas, allowing it to sink toward the center. Inflowing gas can reach high densities, forming massive star clusters and igniting what astronomers call a starburst, a period when the galaxy forms stars at a rate far higher than normal. In some mergers, dust becomes so abundant that much of this star formation is hidden in visible light, but it glows strongly in the infrared as dust absorbs ultraviolet and optical light and re-emits it as heat. Observations with infrared telescopes have identified galaxies in merger-driven starbursts that are astonishingly luminous in the infrared, often called luminous infrared galaxies or ultra-luminous infrared galaxies. Their brilliance is not a sign of calm maturity. It is a sign of gas being violently rearranged and rapidly turned into stars. Yet even a starburst does not last forever. Gas is consumed. Supernova explosions inject energy into the surrounding medium. Winds and outflows can remove gas from the galaxy, especially when the system is still building, and gravitational wells are not yet as deep as they will become later. Over time, the starburst fades, leaving behind a galaxy with less cold gas, older stars, and a smoother overall structure. This is one reason elliptical galaxies often appear redder than spirals. With less ongoing star formation, fewer bright blue massive stars are present, and the light becomes dominated by longer-lived, cooler stars. Major mergers also do something else that is quietly central to the birth of galaxies as a whole. They help build the engines that sit at galactic centers. Most massive galaxies host supermassive black holes at their cores, with masses ranging from millions to billions of times the mass of the Sun. These black holes are not decorative curiosities. They are deeply tied to galaxy evolution. Evidence for that connection appears in relationships like the M-sigma relation, which links the mass of the central black hole to the velocity dispersion of stars in the galactic bulge. In simple terms, the more massive the bulge, and the more vigorously stars move within it, the more massive the central black hole tends to be. The relationship suggests co-evolution, as if the growth of the black hole and the growth of the galaxy are part of the same slow negotiation. The question then becomes how such black holes formed in the first place, and how they grew so quickly in the early universe. This is still one of the most active areas in astrophysics because observations reveal quasars less than 1 billion years after the Big Bang, powered by black holes already approaching 1 billion solar masses. Building something that massive so early is difficult without sustained feeding. Several pathways are considered plausible for the formation of the first black hole seeds. One possibility is that the earliest massive population 3 stars collapsed into black holes of tens of solar masses. Another possibility is direct collapse, where a large, dense gas cloud collapses into a black hole of perhaps 100,000 solar masses without fragmenting into many stars first. Direct collapse requires special conditions, including strong ultraviolet backgrounds that suppress molecular hydrogen cooling and prevent fragmentation, allowing a larger mass of gas to collapse coherently. Both scenarios are studied using simulations and theoretical modeling, and both may contribute in different environments. Whatever the initial seed, growth requires accretion. A black hole grows when gas falls toward it and loses enough angular momentum to cross the event horizon. But gas rarely falls straight in. It spirals, forming an accretion disk. In that disk, friction and magnetic turbulence transport angular momentum outward, allowing matter to drift inward. As gas compresses and heats in the inner disk, it radiates enormous amounts of energy, often in ultraviolet and X-rays. This radiative output is what makes active galactic nuclei and quasars so luminous. One of the most striking discoveries in astronomy came in 1963, when Martin Schmidt identified the nature of quasars as extremely distant objects with enormous redshifts, implying vast luminosities. The implication was that something compact and extraordinarily powerful was converting gravitational energy into radiation. Accreting supermassive black holes provide the best explanation. Accretion cannot increase without limit because intense radiation pushes back on the inflowing gas. There is a balance point known as the Eddington limit, described by Arthur Eddington, where the outward force from radiation pressure on electrons balances the inward pull of gravity on the gas. When a black hole accretes near this limit, it can grow rapidly, but there is still a characteristic timescale. Under sustained near-Eddington accretion with typical radiative efficiencies, black hole mass increases exponentially with a doubling time of tens of millions of years, often discussed in terms of the Salpeter time after Edwin Salpeter. In cosmic terms, tens of millions of years is fast, but it still requires sustained feeding over long stretches to grow from a small seed to 1 billion solar masses. This is where galaxy mergers return as a crucial part of the story. Mergers are efficient at driving gas inward. Gravitational torques during a merger can remove angular momentum from gas and funnel it toward the center. The same inflow that triggers a starburst can also feed the central black hole. In this way, mergers can light up both stellar and black hole activity at once. A galaxy can become a starburst and an active galactic nucleus in the same event, powered by the same rearrangement of gas. Over time, as the central black hole grows, its influence expands beyond the immediate accretion disk. This influence is not gravitational on galactic scales, because even a billion solar mass black hole is still a small fraction of the galaxy's total mass. The influence is energetic. Active galactic nuclei can launch winds and jets. These outflows can heat surrounding gas, expel it, or prevent it from cooling. This is known as active galactic nucleus feedback, and it is a leading explanation for why massive galaxies often stop forming stars. When feedback keeps gas hot, it cannot collapse into molecular clouds, and star formation declines. There are different modes of this feedback. In a radiative mode, intense light and winds from a luminous accretion disk can push gas outward. In a jet mode, collimated relativistic jets can inject energy into the surrounding halo and intracluster medium, inflating bubbles of hot gas and preventing cooling flows. X-ray observations with telescopes such as the Chandra X-ray Observatory have revealed cavities in hot cluster gas associated with jets from central active galaxies, providing direct evidence that black holes can influence gas far beyond the scale of the accretion disk. This connection between black holes and galaxies helps explain a slow, large-scale trend. As galaxies grow more massive, their black holes tend to grow as well. As black holes grow, feedback becomes more effective. As feedback becomes more effective, it can suppress the formation of new stars by heating or removing cold gas. The galaxy shifts from a blue, star-forming system to a redder, more quiescent one. This transition does not happen overnight. It is a gradual outcome of repeated cycles of accretion, star formation, and feedback across billions of years. The growth of black holes is also inferred statistically through what is known as the Sultan argument, proposed by Andrei Sultan in the 1980s. By integrating the total light emitted by quasars over cosmic history, astronomers estimate the total mass that must have been accreted onto black holes, because quasar light is powered by accretion. The result aligns broadly with the black hole mass density observed in nearby galaxies today, supporting the idea that most supermassive black hole growth occurs during luminous accretion phases. In the context of the slow birth of galaxies, this means the universe is not only assembling stars and disks, it is also assembling central engines that will later regulate those stars and disks. The emergence of ellipticals through mergers and the growth of supermassive black holes through accretion are not separate stories. They are intertwined threads. A major merger can transform a disk into an elliptical and simultaneously trigger a starburst and feed a central black hole. The starburst enriches gas, produces supernovae, and consumes fuel quickly. The black hole grows and may power an active galactic nucleus whose feedback heats the remaining gas. When the event is over, the remnant galaxy may be larger, smoother, more bulge-dominated, and less able to form new stars rapidly. Over cosmic time, repeated events of this kind help build the population of massive elliptical galaxies observed in the present-day universe. This also helps explain why the most massive galaxies tend to be the least star-forming. Their histories include many mergers. Their halos are deep. Their gas can be heated to high temperatures and kept hot by feedback. Their black holes are massive enough to maintain that state. The end result is a galaxy that shines mostly with older stars, glowing steadily rather than bursting with new ones. Yet none of this is instantaneous. Even the most dramatic merger unfolds over hundreds of millions of years. The inflow of gas, the triggering of starbursts, the growth of the black hole. the launching of winds, the settling of stars into a new configuration. All of it is slow on human timescales. The word violent in violent relaxation describes the intensity of gravitational rearrangement, not its speed in everyday terms. The universe has time. It does not need to hurry. There is a calm perspective hidden in this. A smooth elliptical galaxy may look like the quietest form a galaxy can take, but it can also be the fossil of turbulence. Its smoothness can be the final resting shape of many past collisions. And a supermassive black hole, invisible by nature, can be the record keeper of a galaxy's feeding history, its mass reflecting how much gas has been driven inward over billions of years. So as the early universe continues to mature, the landscape of galaxies becomes more diverse. Some systems manage to protect their disks and continue forming stars steadily. Others are transformed by major mergers into spheroids. Many experience a mixture, building bulges through minor mergers and internal instabilities while still retaining some disk structure. Across this diversity, supermassive black holes grow alongside their hosts, sometimes quietly, sometimes in blazing quasar phases visible across the observable universe. The slow birth of galaxies is therefore not only about building light, it is about reshaping it. It is about gravity not merely collecting matter, but rearranging it through mergers. It is about cooling and rotation building disks, and then interactions erasing them. It is about stars forging heavy elements and black holes, regulating the future supply of cold gas. Over billions of years, the universe builds, disrupts, rebuilds, and regulates, creating galaxies that are not born in a single moment, but assembled through long sequences of events, each leaving a trace in structure, chemistry, and central engines that still persist today. As galaxies continue to assemble, a strange pattern becomes visible when looking across the whole universe instead of at any single system. Star formation does not simply rise forever as galaxies grow. It rises, reaches a broad peak, and then begins to ease off, as if the universe itself had a youthful phase of frantic productivity before settling into something calmer. This pattern is not guessed. It is measured by looking at galaxies at many different distances, which also means many different times, because light takes time to travel. The basic method is beautifully simple. A telescope sees distant galaxies as they were long ago. A nearby galaxy is seen as it was recently. A very distant galaxy is seen as it was when the universe was young. By collecting huge samples at different redshifts and estimating how quickly those galaxies are forming new stars, astronomers can reconstruct how the average star formation rate of the universe changed over cosmic time. In the 1990s, researchers including Piero Madao and Simon Lilly helped establish this history by compiling star formation measurements across redshift. The result is often called the cosmic star formation rate density, and it has a characteristic shape. Star formation rises for the first few billion years, reaches a peak when the universe is only a few billion years old, roughly around 10 billion years ago, and then declines toward the present. The exact height and timing of the peak depend on the details of measurement and dust correction. But the broad message is consistent across multiple surveys and methods. The universe was once forming stars at a rate several times higher than it is now. That peak is not mysterious if the listener keeps one idea close. Stars are made from cold, dense gas. Star formation is not primarily limited by a lack of gravity. It is limited by whether galaxies can gather cold gas, keep it cold and compress it into molecular clouds. In the early universe, gas is abundant and accretion from the cosmic web is vigorous. Halos are merging rapidly. Disks are gas-rich. Galaxies are constantly being fed. In that environment, star formation can run high for long stretches, interrupted by feedback, but repeatedly reignited by fresh inflows. As time passes, several slow processes begin to reduce that supply. One is simple consumption. Gas becomes stars, and while many stars return some material through winds and explosions, much of the mass becomes locked in long-lived stars and compact remnants. Another is heating. Supernovae and active galactic nuclei inject energy into gas, keeping it warm or expelling it from galaxies, which reduces the amount of cold molecular material available for new stars. A third is environment. In dense regions such as galaxy clusters, galaxies can lose gas through ram pressure stripping and other interactions, cutting off star formation from the outside in. Inside galaxies, star formation tends to follow a relationship discovered and refined over decades. In the 1950s, astronomer Martin Schmidt proposed that star formation rates are connected to gas density. Later, Robert Kennicott demonstrated a strong empirical link between the surface density of gas and the surface density of star formation in disk galaxies, often referred to as the Kennicott-Schmidt law. In calm words, it says that regions with more dense gas form stars more quickly, and regions with less dense gas form stars more slowly. This is not a strict rule without scatter, and it changes with environment, but it captures a fundamental truth. Star formation is tied to the local supply of dense molecular gas. That supply is controlled by cooling and by chemistry, which brings the story into chemical enrichment. The earliest gas was mostly hydrogen and helium, but once stars exist, the universe begins a slow, cumulative transformation. Every generation of stars alters the chemical makeup of the next. The physics behind this was laid out in the mid-20th century through the development of stellar nucleosynthesis theory, including the landmark work of Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle in 1957. Their synthesis helped explain how the elements are built inside stars through successive nuclear burning stages and through neutron capture processes. A star is not only a light source, it is a chemical machine. Massive stars fuse hydrogen into helium, then helium into carbon and oxygen, then move on toward heavier elements in layered shells. When they explode as Type II supernovae, they eject large amounts of oxygen, neon, magnesium, silicon, and other so-called alpha elements, along with some iron. These explosions also drive shocks into the surrounding interstellar medium, stirring gas and triggering new rounds of collapse in some regions while disrupting it in others. Type I. A supernovae contribute a different chemical signature. These events occur when a white dwarf in a binary system gains mass from a companion star, or merges with another white dwarf, reaching conditions where runaway thermonuclear burning can occur. Type I supernovae produce large amounts of iron and iron peak elements. They also tend to occur with a delay because they require stars to evolve into white dwarfs and then reach explosive conditions. This delay means that the chemical enrichment of galaxies unfolds in time-layered ways. Early star formation enriches gas quickly with alpha elements from massive stars. Later, iron from Type I supernovae becomes more prominent. There is another important contributor, asymptotic giant branch stars, often called AGB stars. These are intermediate mass stars that shed their outer layers through strong winds late in life. They enrich the interstellar medium with elements like carbon and nitrogen and contribute to dust formation. Dust matters because it helps shield molecular clouds from radiation, allowing molecular hydrogen to persist. And it also provides surfaces on which some molecules form more efficiently. Dust is, in a quiet way, a star formation enabler. All of this builds toward a key idea. Chemical enrichment makes cooling easier. Cooling makes fragmentation easier. Fragmentation changes the masses of stars that form. In the earliest metal-poor conditions, gas struggles to fragment into small clumps, encouraging the formation of more massive stars. As metals and dust accumulate, gas can cool to lower temperatures and break into many smaller clumps, producing more low-mass stars. The distribution of stellar masses at birth is known as the initial mass function. Edwin Salpeter proposed an early form of this distribution in 1955. Modern versions refine the details, but the essential concept remains. The universe gradually shifts from an early epoch likely biased toward very massive stars, to later epochs where a wide range of masses form, including many small stars that will outlive the current age of the universe. This gradual change does not just affect individual stars, it changes how a galaxy evolves. Massive stars produce intense ultraviolet radiation and strong winds, shaping the interstellar medium quickly. They also explode quickly, injecting energy and metals. Low-mass stars are quieter but long-lived, building up the stellar mass of a galaxy over billions of years. As galaxies chemically mature, their star formation becomes more efficient in some ways, but it can also become more self-limiting, because the same enrichment that helps cooling also enables more dust, more radiation absorption, and complex feedback cycles. The tools used to measure these processes are as important as the processes themselves, because star formation is not always visible in obvious light. Young, massive stars emit strongly in ultraviolet wavelengths, but dust absorbs much of that light and re-emits it in the infrared. This is why infrared observatories have been essential for building the cosmic star formation history. Telescopes like the Spitzer Space Telescope and the Herschel Space Observatory have helped measure the dust-obscured side of star formation, ensuring that the universe's most productive phases are not underestimated simply because they are hidden behind dusty curtains. At the same time, facilities like the Atacama Large Millimeter Array, ALMA, observe cold gas and dust directly at millimeter wavelengths. ALMA can detect molecular gas tracers and dust emission in distant galaxies, revealing reservoirs of star-forming material in systems seen as they were billions of years ago. In a sense, ALMA shows the fuel, while ultraviolet and infrared observations show the fire. These measurements make another pattern clear. The decline in cosmic star formation is linked to the slow reduction of available cold gas and the slow rise of mechanisms that keep gas hot. In many galaxies, feedback from supernova is enough to regulate star formation without shutting it down entirely. Supernova explosions carve bubbles in the interstellar medium, drive turbulence, and launch winds. In small galaxies, these winds can escape easily, removing gas and lowering star formation for long periods. In larger galaxies, the gas is harder to remove, but it can be heated and stirred, preventing runaway collapse. In the most massive galaxies, feedback from supermassive black holes becomes increasingly important. When a central black hole is active, the energy released by accretion can heat surrounding gas and prevent it from cooling into the galaxy, a process often called quenching. This is one reason many massive elliptical galaxies contain old stellar populations and form few new stars today. Their gas exists, but it is often too hot and too diffuse to collapse efficiently. The combined effect of consumption, feedback, and environmental stripping produces a universe that becomes less star-forming over time. This does not mean star formation stops. It means the average pace declines. Some galaxies, including many disk galaxies, continue forming stars steadily for billions of years. Others undergo bursts triggered by mergers or inflows. Others fade into quietness after losing their gas or heating it beyond easy recovery. Chemical enrichment continues through all these phases, but its character changes. Early on, enrichment can be rapid in localized regions because massive stars explode quickly. Over time, enrichment becomes more widespread and mixed. Galaxies develop gradients with higher metallicity, often towards centers, where star formation has been sustained and gas has been processed repeatedly, and lower metallicity toward outskirts, where gas can be more pristine or diluted by infall. This is where the slow birth theme returns with extra weight. A galaxy is not born once. It is born many times, chemically speaking. Each generation of stars is both a product and a cause. Stars form from the chemistry of earlier stars, and then they alter that chemistry again. A galaxy gradually becomes a more complex chemical ecosystem, and that complexity affects everything from cooling rates to dust content to the kinds of planets that can form later. There is also a quiet continuity between the cosmic scale and the local scale. The cosmic star formation history tells what the universe did on average. Chemical enrichment tells how that average becomes embodied in real places. A single galaxy's history is a particular path through that broader trend, shaped by its merger history, its environment, its halo mass, and its feedback cycles. Some galaxies peak early and fade, others grow steadily and peak later. Some are rejuvenated by fresh gas. Others are shut down by hot halos and black hole feedback. In every case, the pace is slow because the universe is working with large distances, low densities, and processes that require many cycles. Gas must travel along filaments. It must cool. It must settle. It must fragment. Stars must live and die to enrich gas. The enriched gas must mix and recollapse. The feedback must fade before collapse resumes. Even when things feel intense, like a starburst, the full impact unfolds across tens or hundreds of millions of years, and the long-term trend unfolds across billions. By the time this broader pattern is appreciated, the listener can feel the shape of the whole story more clearly. The slow birth of galaxies is not only the slow gathering of matter in the early universe. It is the slow rise and fall of star formation across cosmic history, and the slow accumulation of the elements that make galaxies more efficient at cooling and more capable of complex structure. It is a universe that begins chemically simple, becomes richer through stellar alchemy, and then gradually quiets as its easiest fuel is consumed, heated, or removed, leaving behind the mature galaxies seen today, still evolving, still changing, but doing so with the measured, patient tempo that the cosmos seems to prefer. By now, the universe has done something quietly remarkable. It has taken a nearly uniform beginning and turned it into a landscape. Not a landscape of hills and valleys in the usual sense, but a landscape of density, where matter is gathered into filaments, poured into knots and drained away from immense, empty regions. This is the large-scale structure of the universe, and it is not guessed from theory alone. It is mapped. When astronomers chart the positions of galaxies across enormous distances, they find that galaxies are not sprinkled evenly through space. They clump, they form chains, they gather into walls and filaments that stretch across hundreds of millions of light years. Between these structures are voids, vast regions with far fewer galaxies. This arrangement is often called the cosmic web, and it is one of the most direct, visible signatures of the universe's underlying dark matter scaffolding. Surveys have been central to revealing this pattern. The Sloan Digital Sky Survey, which began at the turn of the 21st century, mapped millions of galaxies and produced a three-dimensional view of the nearby universe on truly vast scales. Later programs, including the Dark Energy Survey, expanded and refined this mapping, improving measurements of clustering and gravitational lensing. These surveys do not merely create pretty plots. They allow astronomers to measure how strongly galaxies cluster as a function of scale, which in turn reveals information about the growth of structure over cosmic time and the balance between matter and dark energy. One of the most elegant features embedded in this structure is the imprint of baryon acoustic oscillations. In the early universe, before recombination, ordinary matter and radiation behaved like a coupled fluid. Pressure waves, essentially sound waves, traveled through that hot plasma. When the universe became neutral and transparent, those waves froze into the distribution of matter as a preferred scale, a subtle tendency for galaxies to be separated by a characteristic distance. By measuring this scale in galaxy surveys, cosmologists use it as a standard ruler to probe cosmic expansion. The concept connects the universe's first few 100,000 years directly to the arrangement of galaxies billions of years later, as if an ancient rhythm still echoes in the spacing of modern structure. Gravitational lensing provides another window into the cosmic web, and it is especially important because it traces mass directly, not just light. According to Albert Einstein's general theory of relativity, mass curves space-time and bends the paths of light rays. When light from distant galaxies passes through the gravitational field of intervening structures, the images are distorted. In strong lensing, this can produce arcs, rings, or multiple images. In weak lensing, the effect is subtle, detectable only statistically across many galaxies. But weak lensing maps reveal where mass is concentrated, including mass that does not shine. This is one of the ways astronomers build mass maps that align beautifully with the idea that galaxies live in a larger dark matter framework. All of this reinforces a central theme. Galaxies are not isolated islands floating in featureless space. They are nodes in a network. They grow by pulling material along that network, and the network itself grows as gravity continues amplifying the early fluctuations. On the larger scales, the cosmic web becomes more pronounced with time in a universe dominated by cold, dark matter. On very late timescales, dark energy begins to slow the growth of new structure because accelerated expansion makes it harder for distant regions to collapse together. But within already bound structures, gravity continues to operate. Clusters remain bound. Groups remain bound. Galaxies keep orbiting, merging, and evolving. Inside that immense structure, one particular galaxy matters for a different reason. Not because it is special to the universe, but because it is where the listener is. It is the Milky Way. The Milky Way is a spiral galaxy with a central bulge, a rotating disk, and a surrounding halo of dark matter that extends far beyond the visible stars. The disk is divided into a thin disk, where many young stars and star-forming regions live, and a thick disk containing older stars with different orbital properties. Beyond the disk is a stellar halo, a diffuse population of stars orbiting in many directions, often containing remnants of past mergers. And beyond even that, invisible but dominant in mass, lies the dark matter halo. The Milky Way did not form as a single object in one uninterrupted collapse. It assembled gradually through the same hierarchical processes that shaped galaxies across the cosmic web. Gas accreted along filaments. Small galaxies merged in. Stars formed in bursts and lulls. The disk settled over long periods. The bulge built up through internal processes and interactions, and a faint but persistent rain of small satellites continued to add mass over billions of years. One of the most powerful tools for reconstructing this history is the European Space Agency's Gaia mission. Gaia does not take glamorous deep-field images. It measures positions, distances, and motions for an enormous number of stars with extraordinary precision. By tracking how stars move, Gaia reveals substructure, streams, and coherent groups that betray their origins. If the Milky Way had formed in isolation, its stars would be mixed more smoothly. Instead, Gaia shows that the halo in particular contains stellar populations with shared motion patterns and shared chemical traits, like scattered pages from different books mixed into a single library. A galaxy merger leaves two main kinds of evidence. One is dynamical, meaning the orbits and motions of stars. The other is chemical, meaning the abundances of elements in those stars. Stars formed in a small dwarf galaxy often have distinct chemical signatures compared with stars formed in a larger system, because their star formation histories differ. Smaller galaxies may enrich more slowly, producing different ratios of alpha elements to iron, reflecting the balance between Type II supernova and Type Ia supernova over time. When such a galaxy is accreted, its stars carry that chemical fingerprint into the larger halo. One of the most discussed events revealed through Gaia data is often called Gaia Enceladus, also nicknamed the Gaia sausage, because of the distinctive elongated distribution of stellar velocities in certain analyses. This refers to a major merger in the Milky Way's early history, likely occurring roughly 10 billion years ago when a substantial dwarf galaxy collided with a young Milky Way. The merger contributed a significant fraction of the inner halo stars, and likely played a role in heating and thickening the early disk. The details are still refined through ongoing research, but the broad conclusion is clear. The Milky Way is, in part, built from other galaxies. The Milky Way continues to grow today, although more slowly than in its youth. It is currently in the process of disrupting the Sagittarius dwarf galaxy, a small satellite galaxy whose stars are being stretched into a long stream that wraps around the Milky Way. This stream is not a dramatic explosion. It is a slow unthreading. With each orbit, tidal forces pull more stars away, and the debris spreads along the satellite's path. Over time, the remnant becomes less a galaxy and more a smear of memory. The Large Magellanic Cloud and the Small Magellanic Cloud are also part of this story. They are not just bright patches in the southern sky. They are substantial satellite galaxies interacting with the Milky Way. Their gravitational influence can stir the Milky Way's outer disk, and their eventual fate may involve merging into the Milky Way over future billions of years. The exact timeline depends on their orbits and on dynamical friction within the Milky Way's dark matter halo. But the direction is the same as it has always been in hierarchical growth. Larger systems absorb smaller ones. Gas accretion matters just as much as mergers. The Milky Way forms stars primarily in its disk, in regions rich in molecular gas. Maintaining star formation over billions of years requires replenishment, because star formation consumes cold gas. Some replenishment comes from stellar winds and supernova ejecta, recycling material back into the interstellar medium. But continued star formation at the Milky Way's present pace also points to ongoing gas inflow, likely from the circumgalactic medium, the extended halo of gas surrounding the galaxy, and from the broader intergalactic medium along filaments. This surrounding environment is difficult to observe directly because much of the gas is hot and diffuse, but it can be detected through ultraviolet absorption lines in the spectra of background sources and through emission in certain bands. The circumgalactic medium acts as both reservoir and regulator. It stores baryons that are not in stars and not in the disk, and it is shaped by outflows from supernovae, and, to a lesser extent in the Milky Way today, by central activity. In more active galaxies, outflows can be strong enough to enrich the circumgalactic medium with metals, spreading chemical complexity beyond the disk itself. The Milky Way also contains a supermassive black hole at its center, Sagittarius A star, with a mass of about 4 million times the mass of the Sun. Compared to the black holes powering quasars, Sagittarius A star is quiet today. It is not currently swallowing matter at a dramatic rate, yet it still represents an important aspect of the Milky Way's history, because its existence implies that the galaxy has experienced phases of accretion and central activity in the past. Even if those phases were modest, they connect the Milky Way to the broader pattern of black hole and galaxy coevolution. The slow assembly of the Milky Way is therefore a local example of the universal process, but it carries an extra clarity because it can be studied star by star. In distant galaxies, a telescope sees integrated light, the blended glow of billions of stars. In the Milky Way, individual stars can be dated, their motions measured, their chemical compositions analyzed. The galaxy becomes an archaeological site. Each population is a layer. Each stream is a fracture line. Each cluster is a preserved piece of an earlier time. And there is an even wider perspective that loops back to the cosmic web. The Milky Way is not alone. It resides in the local group, a small collection of galaxies dominated by the Milky Way and the Andromeda Galaxy, also called Messier 31. Andromeda is a spiral galaxy somewhat larger than the Milky Way, and it is not just a distant neighbor, it is approaching. Measurements of Andromeda's motion indicate that it is moving toward the Milky Way at roughly 100 kilometers per second along the line of sight, with a transverse component that still carries uncertainty but appears consistent with an eventual collision. Over approximately 4 billion years, the two galaxies are expected to interact, pass through each other, and then merge. This will not be a head-on crash in the everyday sense. Stars will mostly pass by other stars without direct collisions. But the galaxy's gravitational fields will distort their disks, pull out tidal tails, and stir gas into new star formation episodes. Over time, the combined system will likely relax into a large elliptical or spheroidal galaxy, depending on how much cold gas remains and how feedback shapes the final outcome. That future merger is not an unusual fate. It is the continuation of the same process that formed the Milky Way in the first place. Galaxies grow by accretion and merging. Their environments guide their interactions. The cosmic web channels matter. Clusters and groups assemble. Dark matter halos deepen. Over long timescales, local gravity wins inside bound structures, even as the universe expands overall. Seen from far away, the Milky Way story is just one thread in a vast tapestry of large-scale structure. Seen from within, it is the nearest example of the slow birth of galaxies, with evidence scattered across the sky in streams of stars and in the chemical fingerprints inside ancient stellar populations. There is also a quiet humility in this. The Milky Way's disk feels stable in a night sky. It feels like home, but it is a temporary arrangement in cosmic terms, an evolving structure shaped by past mergers and future encounters. The stars in the disk orbit the center on timescales of hundreds of millions of years. The galaxy itself changes over billions. The halo continues to absorb debris. The outer disk ripples. The gas supply cycles between phases. The chemical makeup grows more complex. And the large-scale structure around it is doing the same. Filaments continue to guide galaxy motions. Groups continue to fall together. Clusters continue to grow at the nodes of the cosmic web. Voids continue to expand and empty out. Dark energy continues to accelerate the expansion of space on the largest scales, gradually isolating bound structures from one another over the far future. The universe becomes, in some sense, more separated with time, but within the islands that remain bound, evolution continues. So the story of galaxies is never only about the first galaxies turning on. It is also about the slow growth of the web that connects them and the slow assembly of particular systems within it. The cosmic web is the universe's largest structure, and the Milky Way is a small, luminous node within that network. Both are products of the same beginning. Tiny fluctuations in density, amplified over vast times by gravity, shaped by cooling, enriched by stars, and reorganized by mergers. And when looking up at the hazy band of the Milky Way across the night sky, it becomes possible to hold two scales at once. A local river of starlight made of billions of suns, and a larger web beyond it, made of countless other galaxies, all born slowly from a universe that started out almost perfectly smooth. The Milky Way feels intimate because it is close, but it is also only one kind of neighborhood. Step outward from a small group like the local group, and the universe becomes increasingly social. Galaxies gather into groups, and groups gather into clusters, and clusters sit at the thickest intersections of the cosmic web like knots in a vast net. In these regions, space is still enormous and mostly empty, but compared to the lonely outskirts of filaments, clusters are busy. They are places where galaxies live under constant gravitational pressure, where the environment is not a background detail, but a shaping force. A galaxy cluster is not just a collection of galaxies. It is a single, massive gravitational system dominated by a shared dark matter halo. The galaxies are the visible ornaments, but most of the mass is invisible. Typical rich clusters contain hundreds to thousands of galaxies, and the total mass, including dark matter, can exceed 100 trillion times the mass of the Sun. That mass creates a gravitational potential well deep enough to hold not only galaxies, but also a huge reservoir of gas heated to tens of millions of degrees Kelvin. This gas is called the intra-cluster medium, and it is so hot that it shines in X-rays. Space-based telescopes like the Chandra X-ray Observatory and XMM Newton have mapped this hot plasma, revealing that much of a cluster's ordinary matter is not locked in stars at all, but floating between galaxies as a thin, glowing atmosphere. The intracluster medium matters because it interacts with galaxies in a way that intergalactic space usually does not. When a spiral galaxy moves through a cluster, it is not drifting through a vacuum. It is plowing through a diffuse but extremely hot gas. That motion creates a pressure on the galaxy's own interstellar gas, especially the cold gas in the disk that would otherwise form stars. This is RAM pressure stripping, first described in a widely used form by Eugene Gunn and J. Richard Gott in the early 1970s. The idea can be stated plainly. If the external pressure from the intra-cluster medium pushing on the galaxy's gas becomes stronger than the gravitational pull holding that gas in the disk, the gas is stripped away. This can happen gradually or dramatically depending on the galaxy's speed, the density of the intra-cluster medium, and the depth of the galaxy's own gravitational well. Observationally, it can produce spectacular tails of gas streaming behind galaxies, sometimes extending tens of thousands of light years. In those tails, star formation can even occur in pockets where gas is compressed, creating strings of young star clusters outside the main disk. But the long-term effect is usually quenching. Remove the cold gas, and the galaxy loses its ability to form new stars. Its bright blue massive stars die out within tens of millions of years, and the galaxy's light shifts toward redder hues, dominated by longer-lived stars. Clusters also affect galaxies through repeated gravitational encounters. Direct slow mergers between large galaxies are less common in the densest cluster regions because galaxies move quickly relative to each other, often at speeds of around 1,000 kilometers per second. At those speeds, galaxies tend to fly past rather than bind together, but even fast flybys can do damage. Tidal forces can disturb disks, trigger bursts of star formation by compressing gas, or heat stellar orbits, gradually transforming a thin disk into a thicker, more spheroidal system. This cumulative process is sometimes called galaxy harassment, a term used to describe the effect of many rapid encounters over time. There is also strangulation, sometimes called starvation, where a galaxy's outer reservoir of gas is removed or prevented from accreting, even if the disk gas is not stripped immediately. A galaxy can continue forming stars for a while by consuming its remaining cold gas, but without replenishment, it slowly runs down. The galaxy does not need to be violently stripped to be quenched. It can simply be cut off from its supply lines. The results of these environmental processes appear in broad population trends. Dense environments like cluster cores contain a high fraction of elliptical and lenticular galaxies, while lower density environments like the field contain more star-forming spirals. This is closely related to what is known as the morphology-density relation, explored in influential 20th century work by astronomers such as Alan Dressler. The basic observation is that galaxy shape and galaxy environment are correlated. It is not that clusters magically create ellipticals out of nothing. It is that clusters favor processes that heat disks, remove gas, and end star formation. And these processes naturally produce smoother, redder, more spheroidal galaxies. Even the history of clusters reflects the slow birth theme. Clusters grow over billions of years as groups fall together along filaments and merge. When clusters collide, it can produce shock fronts in the hot gas that stretch across millions of light years. One of the most famous systems in this context is the bullet cluster, where X-ray observations show the hot gas displaced from the main mass distribution inferred through gravitational lensing. The lensing mass peaks align more closely with the galaxy distributions than with the gas, indicating that most of the mass is in a component that passed through the collision without being slowed like the gas. This is powerful evidence for dark matter because it shows mass behaving differently from ordinary matter under collision conditions. Clusters also host the most massive galaxies, often sitting at their centers. These brightest cluster galaxies can grow through repeated mergers over long periods and through the accretion of stars from disrupted satellites. Their environments are rich in hot gas, and that introduces another slow puzzle. Hot gas in a cluster radiates energy in X-rays. In principle, if it cools enough, it should flow inward toward the center and form stars in a cooling flow. For decades, observations suggested the gas should be cooling faster than the observed star formation rates allowed. The solution involves feedback, especially from active galactic nuclei. Jets from central supermassive black holes can inject energy into the intra-cluster medium, inflating cavities and generating sound waves and turbulence that help prevent runaway cooling. In this way, black hole feedback shapes not only individual galaxies but the thermal history of an entire cluster atmosphere. So clusters represent a kind of extreme laboratory. They magnify processes that also occur elsewhere, but in a harsher setting. They show how environment can suppress star formation by removing gas, how repeated encounters can alter morphology, and how dark matter dominates the gravitational architecture. They also show that the slow birth of galaxies is never just about a galaxy in isolation. It is also about where that galaxy lives, what it runs into, what strips its fuel, and what heats its surroundings. From there, the story naturally shifts from what the universe does to how it is studied. Because the cosmic web, clusters, and galaxies are all part of one connected gravitational system, and no single observation can capture the whole time sequence. Telescopes provide snapshots at different epochs, but to connect those snapshots into a continuous physical narrative, astronomers rely on simulations. Simulations are not decorative. They are one of the main ways the slow birth story becomes testable. A modern cosmological simulation begins with initial conditions derived from the early universe, especially from measurements of the cosmic microwave background by experiments and missions such as the Planck satellite. Those measurements constrain the composition of the universe, including the amount of ordinary matter, the amount of dark matter, and the amount of dark energy, as well as the size distribution of primordial fluctuations. With those inputs, a simulation can create a virtual universe in which matter is distributed in a pattern statistically consistent with the early fluctuations. The first step is often an n-body simulation, where dark matter is represented by a huge number of particles that interact through gravity. As the simulation evolves, those particles clump, merge, and form halos, building a cosmic web that looks strikingly similar to the web traced by real galaxies. This is the gravitational backbone, It captures the growth of structure on large scales extremely well because dark matter is dominated by gravity and behaves in most models as a collisionless component. But galaxies are not made of dark matter alone. They are made of gas and stars and radiation and magnetic fields, and this is where simulations become more complicated. Gas dynamics require hydrodynamics, the physics of fluids. In cosmological simulations, gas is usually modeled with either smoothed particle hydrodynamics or grid-based methods, both of which have strengths and weaknesses. The gas falls into dark matter halos, shocks, heats, cools, and can form dense clouds. In principle, if everything could be computed down to the scale of individual stars, a simulation could follow star formation directly from gas fragmentation. In practice, the required resolution is far beyond what can be done for a representative volume of the universe. So simulations use what are called subgrid models. These are recipes that approximate small-scale physics within a larger-scale calculation. Star formation, for example, might be modeled by converting gas into star particles when it reaches certain densities and temperatures, with rates guided by observed relationships, such as the Kennicutt-Schmidt law. Supernova feedback is modeled by injecting energy, momentum, and metals into surrounding gas. Black hole growth is modeled by seeding black holes in certain halos and allowing them to accrete gas according to physically motivated prescriptions, then returning energy to the environment to represent active galactic nucleus feedback. This is not cheating. It is a necessary compromise. The goal is not to simulate every star individually. The goal is to simulate the correct large-scale outcomes given the limits of computation, and then to compare those outcomes with observations. Several simulation projects have become especially influential in this field. The Millennium simulation focused primarily on dark matter structure formation and provided a backbone for semi-analytical models of galaxies. The Eagle simulation, developed by an international collaboration including researchers in the United Kingdom and elsewhere, explored how different feedback implementations affect galaxy properties. The Illustris project and its later evolution into the Illustris TNG simulations produce large volumes with galaxies whose populations can be compared statistically with surveys. The Fire simulations often run at higher resolution in smaller volumes, focused on detailed feedback processes in individual galaxies, exploring how stellar winds, radiation, and supernova shape star formation and outflows. The power of these simulations is not just that they produce pretty galaxies, it is that they allow controlled experiments. A researcher can adjust the efficiency of supernova feedback and see how galaxy masses change. A researcher can modify the way black holes inject energy and see whether massive galaxies quench correctly. A researcher can test how metal enrichment affects cooling and disk formation. If the simulation produces too many stars too early, or too few disk galaxies, or clusters with the wrong gas properties, that mismatch points to physics that is missing or misrepresented. Simulations also help interpret observations that are otherwise ambiguous. A faint smudge in a deep field image might be a small galaxy, a merging pair, or a system with intense star formation hidden behind dust. A simulation can generate synthetic observations, creating mock images and spectra that can be compared with real telescope data. This makes it possible to connect what is physically happening in the simulation with what an observer would actually see. At the same time, simulations expose the limits of current understanding. Many of the most important processes in galaxy formation involve feedback. And feedback is difficult because it spans scales from individual stars to galactic halos. A supernova explosion occurs on a tiny scale compared with a galaxy, but its collective impact can shape a galaxy's gas content and metallicity. Black hole jets launch from regions smaller than the solar system, yet they can influence gas across hundreds of thousands of light years in clusters. Modeling these cross-scale effects accurately remains one of the central challenges of the field. This is why results are often discussed with careful language. A simulation can match many observed properties while still being wrong in important details, because different feedback prescriptions can sometimes produce similar high-level outcomes. This is also why multiple simulation approaches are valuable. When different codes and methods produce similar broad results, confidence increases that the broad narrative is robust, even if details differ. Recent observations have added fresh pressure to these models in a useful way. The James Webb Space Telescope has revealed galaxies at very high redshift that appear unexpectedly bright, and in some cases, surprisingly massive. This does not necessarily mean the standard picture is wrong. It may reflect how masses are inferred from light, how dust affects observations, or how star formation efficiency behaves in early dense halos. But it does force simulations to confront a sharper question. How quickly can gas cool and form stars in the early universe under realistic feedback? Are some early environments more efficient than expected? Do some assumptions about the first generations of stars need refinement? These are the kinds of questions where simulation and observation push each other forward. Clusters play a role here too, because they provide strong constraints through gravitational lensing, X-ray measurements, and galaxy population statistics. If a simulation produces clusters with gas that cools too fast, it must include stronger feedback. If it produces too many stars in cluster cores, it must regulate star formation more effectively. If it produces the wrong distribution of galaxy morphologies across environments, it must model stripping, mergers, and quenching more accurately. In this way, clusters act like stress tests for galaxy formation physics. The deeper theme is that the slow birth of galaxies is not only slow in time, it is also slow in understanding. Cosmology has made stunning progress, but the universe does not hand over its details easily. Every new instrument, from wide-field surveys mapping large-scale structure to precision missions like Gaia, to deep infrared telescopes like James Webb, forces models to become more honest. Simulations become more sophisticated. Feedback prescriptions become more physically grounded. Comparisons become more direct and statistical. The narrative becomes sharper without losing its core arc. That core arc remains steady. Tiny fluctuations grow under gravity. Dark matter forms halos and filaments. Gas falls in, heats and cools. Stars form, enrich gas and drive winds. Galaxies merge, disks form. Ellipticals emerge, black holes grow, and environments like clusters shape what survives. The cosmic web expands and evolves. The universe is not a machine that produces galaxies in a single burst. It is a patient system that produces them through countless cycles of collapse and regulation, with long pauses, repeated disturbances, and gradual settling. And the way this is known is not by seeing the whole story at once, because no observer can. It is known by building the story from many time slices, testing it against the statistical patterns written into large-scale structure, and running the physics forward in simulations to see whether the same kinds of galaxies, clusters, and webs emerge. In other words, the slow birth of galaxies is not only written in the sky, it is also written in the quiet agreement between evidence and model, where the universe is allowed to be complicated and where understanding advances by patient iteration rather than sudden certainty, much like the galaxies themselves. There is a temptation when looking at a galaxy to think the hardest part is finished. The stars are in place. The spiral arms curve with quiet confidence. The core glows like it knows a secret. It feels complete. But astronomy is full of reminders that completion is often an illusion. Many of the most basic ingredients in the story of galaxies are still not fully identified, and some of the most important moments in their early lives are only partially observed. The outline is strong. The details are still being negotiated. Start with the largest unknown that sits under almost everything: dark matter. The evidence for it is broad and remarkably consistent. Galaxy rotation curves, first made famous through work like Vera Rubin's, show that visible matter cannot account for the gravitational pull in disks. Gravitational lensing maps mass where there is little light. The cosmic microwave background pattern measured by missions like the European Space Agency's Planck satellite fits a universe that contains far more gravitating matter than the atoms alone can supply. Yet the identity of dark matter remains unknown. Many searchers focus on candidates such as weakly interacting massive particles and axions, but no definitive detection has been confirmed. That means galaxy formation is still being modeled around a component that is measured gravitationally, but not yet understood in particle terms. The scaffolding is visible in its effects, but the material of the scaffolding is still unnamed. This uncertainty matters most on small scales, where the structure of dark matter halos intersects directly with the observed structure of dwarf galaxies. Some long-discussed tensions involve the number of predicted small halos, compared with the number of observed dwarf galaxies, and the internal density profiles of dwarf galaxy halos, compared with what simple, cold dark matter simulations might produce. These are not necessarily fatal problems, because ordinary physics can reshape the visible outcome. Supernova feedback can remove gas and reduce star formation, turning many small halos effectively dark. Rionization can suppress collapse of gas into shallow wells. Tidal stripping inside larger halos can alter density profiles. But the fact that these debates persist highlights a broader truth. The smallest galaxies are not just small versions of big ones. They are sensitive probes of both dark matter physics and feedback physics, and they sit right at the boundary where uncertainties have the most leverage. Then there is the question of how gas actually behaves across the halo scales that matter most. The circumgalactic medium, the extended gas reservoir around galaxies, is now understood to contain a large fraction of a galaxy's ordinary matter. It is where inflows and outflows meet. It is the region where supernova-driven winds cool, mix, and sometimes fall back. It is where fresh gas from filaments may arrive and be shock-heated, then either cool into the disk or remain hot for long periods. Observations using ultraviolet absorption lines against background sources and X-ray measurements in massive halos have revealed that this gas exists in multiple phases, with temperatures and densities spanning wide ranges. The circumgalactic medium is not a smooth atmosphere. It is structured, clumpy, turbulent, and time-dependent. Simulations can reproduce many of its broad features, but the details of mixing, cooling, and cloud survival remain challenging. And because this region controls the fuel supply to star formation, uncertainty here feeds directly into uncertainty about how galaxies grow. Rionization also remains a place where the broad arc is clear, and the exact cast of characters is still being sorted. The universe moved from mostly neutral hydrogen after recombination to a mostly ionized intergalactic medium within roughly the first billion years. Evidence comes from cosmic microwave background polarization constraints and from absorption features in the spectra of distant quasars, including the Gunn-Peterson trough at very high redshift. But the question of which sources dominated the rionization photon budget is still being refined. Early massive stars in small galaxies certainly contributed. Low-mass galaxies may have been crucial simply because they were numerous. The escape fraction of ionizing photons, meaning how much ultraviolet radiation actually escapes a galaxy into intergalactic space rather than being absorbed internally, is still a major uncertainty. A small change in escape fraction can shift the rionization timeline noticeably. And the topology of rionization, the patchiness of ionized bubbles across the cosmic web, is still being mapped through ongoing observational programs. Another deep uncertainty lies in the earliest stellar populations. Population 3 stars are expected to have formed from metal-free gas, and they are expected to have been, on average, more massive than later stellar populations because cooling was less efficient. But the exact initial mass function for these first stars is not directly observed. It is inferred from simulations, from chemical signatures in extremely metal-poor stars in the Milky Way halo, and from the broader needs of rionization and enrichment. Small changes to the assumed masses of the first stars change how quickly the universe becomes enriched with heavy elements. How intense the earliest ultraviolet backgrounds are, and how early feedback suppresses further star formation in tiny halos. The first stars are therefore a hinge point, and the hinge is still being tightened. The growth of supermassive black holes is another hinge point with multiple plausible pathways. Quasars seen in the early universe imply that some black holes grew very large, very quickly by cosmic standards. That motivates competing ideas for how the first black hole seeds formed. One path is stellar remnants from very massive early stars, producing seeds of tens of solar masses. Another is direct collapse of gas, producing seeds that might be hundreds of thousands of solar masses under special conditions that suppress fragmentation. Both mechanisms may occur in different environments. What remains uncertain is the relative importance of each, and how often conditions allow prolonged near Eddington accretion without feedback cutting off the supply. The details matter because black hole feedback is one of the main regulators of star formation in massive galaxies and cluster cores. The black holes are not just passengers, they can become governors. Even feedback itself, perhaps the most important internal regulator of galaxies, remains a complex frontier. In broad terms, feedback prevents galaxies from turning all their gas into stars too quickly. Supernovae inject energy, momentum, and heavy elements. Radiation from massive stars heats and ionizes gas. Stellar winds stir turbulence and carve cavities. Active galactic nuclei can drive powerful outflows and jets that heat gas on halo and cluster scales. Most galaxy formation models rely on feedback to reproduce the observed distribution of galaxy masses and star formation rates. Without feedback, Simulations tend to form too many stars too early. With feedback that is too strong, they can suppress star formation too much and fail to build realistic disks. The challenge is not that feedback is optional. The challenge is that feedback is real, multi-scale, and difficult to model with precision. The smallest physical events, like a supernova shock interacting with a molecular cloud, can have consequences that propagate outward into the evolution of an entire galaxy over billions of years. There are also broader cosmological questions that influence how structure grows. Dark energy, discovered through the late 20th century use of Type 1a supernovae as distance indicators, accelerates the expansion of the universe and gradually suppresses the growth of new large-scale structure by making it harder for distant regions to collapse together. Measurements of cosmic expansion are extraordinarily precise in some regimes and still in tension in others, most famously in the so-called Hubble tension, where early universe inferences and local measurements do not always align perfectly. Whether this tension reflects systematic measurement issues or hints at physics beyond the simplest cosmological model remains unsettled. And because the expansion history affects the timing and growth of structure, these cosmological questions reach down into the story of galaxies as well. All of these uncertainties can make the universe feel slippery, as if the story is not finished. But in a more honest sense, the story is finished where it can be finished. The core framework is strong because it is supported by multiple independent lines of evidence. The cosmic microwave background sets the initial conditions. Cold dark matter growth explains the emergence of a cosmic web. Gas physics explains why baryons lag behind dark matter early on and why cooling is a bottleneck. Star formation and nucleosynthesis explain chemical enrichment. Rionization explains the transition from cosmic darkness to a universe filled with starlight. Mergers and angular momentum explain why galaxies come in different shapes. Feedback explains regulation, quenching, and the decline of cosmic star formation over time. The unknowns live mostly in the details of how strongly each process acts in different environments and eras, and in the fundamental identity of the invisible components. And this leads naturally back to the title's quiet insistence. The birth was slow, not because the universe was struggling, but because the physics involved has an inherent tempo. Gravity is powerful, but it is not instantaneous. Collapse depends on density. Early on, density contrasts were tiny, as seen in the 1 part in 100,000 variations of the cosmic microwave background. Small contrasts grow gradually through gravitational instability. Even when halos form, the gas does not immediately become stars, because gas must cool. Cooling is a process of radiating energy away, and radiating energy away depends on atomic and molecular transitions that take time and depend strongly on local conditions. In primordial gas, cooling pathways are limited, which raises the characteristic mass scales of collapsing clouds and slows the first steps toward sustained star formation. Angular momentum adds another break, not by preventing collapse, but by reshaping it. Gas falling into halos carries net spin acquired through tidal torques. Because angular momentum is conserved, gas tends to settle into rotating structures rather than collapsing directly into a point. The formation of disks and the development of stable disk dynamics requires many orbital times. An orbit in the outskirts of a galaxy can take hundreds of millions of years. Even in smaller early systems, settling is not a quick rearrangement. It is the slow redistribution of energy and angular momentum through turbulence, shocks, and cooling. Then there is feedback, which introduces deliberate pauses. When stars form, they do not quietly accept their role as passive residents. Massive stars shine intensely in ultraviolet light. They ionize surrounding gas. They drive winds. They explode as supernovae. In small halos, a single supernova can heat gas enough to delay further star formation for long periods, or even eject gas entirely. In larger halos, feedback does not usually remove all gas, but it keeps the interstellar medium turbulent and multiphase, creating cycles of collapse and disruption. In massive galaxies, black hole feedback can heat halo gas and prevent it from cooling, suppressing star formation for billions of years. These are not rare side effects. They are central to why galaxies do not form all their stars at once. Mergers also slow in a different way. They can be dramatic, but they are not fast. Two galaxies can begin interacting long before they merge, exchanging tidal disturbances over hundreds of millions of years. Major mergers can trigger starbursts and black hole feeding, but the full event is a long gravitational negotiation, ending in relaxation into a new structure. The universe builds big galaxies not by a single collapse, but by many such negotiations. And above all of it, expansion stretches the playing field. The universe expands, and on the larger scales, that expansion gradually becomes accelerated. Structure formation is therefore a race between gravity pulling matter together and expansion pulling distant regions apart. Gravity wins inside bound regions, but the boundaries of what can become bound shift over time. The cosmic web grows, but its growth slows as dark energy becomes more dominant. In that environment, galaxies still evolve, but the formation of entirely new, massive structures becomes less efficient. So the slow birth of galaxies is not a single explanation. It is a layered one. Tiny initial fluctuations, dark matter collapsing first, gas heating as it falls in, cooling as the bottleneck, angular momentum organizing disks, feedback interrupting collapse, mergers rearranging structure over long times, chemical enrichment gradually improving cooling, Rionization heating intergalactic gas and suppressing star formation in the smallest halos. Cosmic expansion setting the overall rhythm. In the end, a galaxy is a record of time expressed as structure. Its halo remembers gravitational growth. Its stars remember chemical history. Its disk remembers angular momentum. Its bulge may remember mergers and instabilities. Its central black hole may remember how often gas was driven inward. Even the empty space around it, filled with the circumgalactic medium, remembers the push and pull of inflows and outflows. And perhaps that is the most calming point of all. The universe did not need urgency to produce beauty. It produced galaxies through accumulation and patience, by letting small advantages compound over long times, by allowing feedback to regulate rather than destroy, and by letting structure emerge in a way that was steady instead of sudden. When looking up at a galaxy's faint light, it becomes possible to hold two truths at once. It is ancient, and it is still becoming. It is a finished shape, and it is also an ongoing process. The slow birth is not a past tense event. It is the universe's preferred way of building anything large, by taking a nearly smooth beginning, adding gravity, adding time, and letting the details assemble themselves piece by piece, across the deep, unhurried scale of cosmic history.